Good morning, good afternoon, and good evening, everyone. My name is Pravesh Koirala, and I will be presenting our paper NP 1 Word Embeddings for Nepali Construction and Evaluation. Word embeddings are not new. However, the availability of corpus and necessary computing powers have sparked an immense interest in them in the past decade. Today, different kinds of word embeddings are in use in applications like classification, semantic analysis, sentiment analysis, and so on. And while the availability of embeddings trained on a large corpus has undeniably propelled the NLP research in resource-rich languages like English, many languages are lagging behind due to the scarcity of adequate resources such as corpus and word embeddings. In this paper, we aim to construct popular contextual and non-contextual word embeddings for Nepali language, the lingua franca of Nepal. We will be focusing on embeddings like word-to-vec, fastText, glove, and BERT. Nepali is a resource-poor language, and thus the availability of the corpus is the primary challenge for construction of word embeddings. However, the recent proliferation of online news portals in Nepal have presented an unexpected source of data. We crawled various Nepali news portals over time and collected more than 700,000 unique news articles, which amounted to 3 GB of text. We obtained another news dataset constructed by Lumsal from the IEEE Dataport website, which was 1.3 GB of Nepali text. Similarly, we also made use of the OSCAR project, which crawls the open web for texts of different languages. And lastly, we also included texts from the Nepali Wikipedia. After deduplication of these sources, we had a corpus with nearly 279 million tokens and near about 3.14 million unique token types. The construction of this large Nepali corpus is one of our major contributions in this work. Moving on, we found it necessary to study how the morphological traits of the Nepali language affects the quality of the embeddings. In Nepali, there are different vowel and consonant sounds which are often pronounced the same but are written and represented in different ways. Due to this phonetic quirk, these vowels and consonants are often mixed up and a single word ends up being written in more than one ways. Moreover, Nepali language has postpositional and agglutinative suffixes which can be compounded together with nouns and pronouns to produce new words. And finally, there are case markers and bound suffixes that primarily inflect verbs. To tackle these challenges, we use three operations, namely normalization, tokenization, and stemming. In normalization, we map different spellings of the same word to one uniform scheme. In tokenization, we split the pre-compound suffixes repeatedly into individual tokens. And in stemming, we remove the inflections to reduce related words to the same stem. Trying these pre-processing schemes in various orders, we derive a total of 8 different corpus. The base corpus, where we do no pre-processing at all. The base normalized corpus, where we normalize the base corpus. The base normalized tokenized corpus, where we first normalize the base corpus and then apply the tokenization, and so on. We use free and open source libraries like Gensim, Stanford NLP's Glove repository, and Hugging Face to train 3 non-contextual word embeddings, word-to-vec, glove, and fastText, of 300 dimensions for each of the 8 corpus. Whereas we only train the BERT corpus on the base normalized token scheme due to resource constraints. In this way, we obtain a total of 25 word embeddings. To evaluate them, we choose 2 different methods. The first one is the intrinsic method. In this method, we manually create a relatedness set and a sentiment set. The relatedness set consists of a total of 42 words divided across topics, namely kitchen topic and nature topic, as you can see in the slides. Similarly, the sentiment set consists of a total of 38 words divided across 2 sentiments, which is positive and negative. We then set k equals to 2 and apply a k-means clustering algorithm to recover 2 known clusters in each of these sets. Once these 2 clusters are obtained, we then calculate their homogeneity by using the purity metric, which ranges from 0 to 1, 0 being the least pure and 1 being the most pure. In extrinsic evaluation, we try a text classification problem. to simulate the scenario of having few data points for any given application, which frankly is a regular use case for resource-poor languages such as Nepali. We train our classification model with limited sample points and test it in large samples. Our classification model is a standard feed-forward neural network with 64 hidden units with ReLU activation and 10 output units with sigmoid activation, trained using the Adam optimizer over the binary cross-entropy loss function. To also measure our results against the baseline, we substitute a trainable keras layer without the word embeddings. We get a few interesting results as you can see in the slides. First of all, we notice that all of the non-contextual word embeddings perform excellently in separating word clusters in the relatedness set, which is represented by the purity of the rel set colon. We notice that the base normalized tokenized scheme achieves the best result in this test. Similarly, the models do not adequately separate sentiment words, which is to say that the embeddings do not recognize positive versus negative sentiments. Interestingly, we observe that the glub-based embeddings perform much better than others in recovering the sentiment of the words, maximum purity being 0.69 of the glub method. Our BERT model does not outperform other word embeddings in intrinsic test, which might not be so unexpected once we consider the fact that we trained it for just one iteration and with a reduced number of parameters. In extrinsic test, we find that the F1 score of embedding layers exceed the baseline by an average of 5%, suggesting that the embeddings indeed do capture semantics that are not present in a limited training set. However, we were surprised to find that the maximum extrinsic F1 score was obtained in the base scheme with no pre-processing at all. Contrary to our expectation, normalization did not seem to affect the results in a substantially positive way. We posit that this may be due to the nature of our corpus, as we derived most of them from authentic news sources which are grammatically sound. We foresee a significant improvement in use cases where data is derived from sources such as social media, tweets, comments, etc., as grammatical mistakes are more frequent in these sources. Another interesting insight is that F1 scores of the fastText model present a lower variation across different pre-processing schemes, demonstrating that it is more invariant to errors such as overstemming. To conclude, we trained a 25-word embeddings model for the Nepali language across different pre-processing schemes and evaluated them using both intrinsic and extrinsic methods, and managed to gain valuable insights that we hope can further the Nepali natural language processing domain. Furthermore, we have made these corpus and models publicly available to actively encourage the Nepali NLP community to make use of and improve upon. We would like to continue our research with more corpus. Specifically, we would like to try and see how an original BERT architecture with a greater number of parameters trained with greater iterations performs in Nepali language. Thank you so much, ladies and gentlemen, for your time. Thank you.